Welcome back and good morning. So indeed, we're going to continue now building some sheaf models. And although the caveat is, you've seen some examples, and I will give you some more. And I'll give you a few constructions that are somewhat more general. But of course, based on what Laurent told us yesterday, we won't be able to build them totally in general for everything. But there's a large class of useful problems that we can address. And those are problems that are of utmost importance for scientific and engineering purposes. So, actually this semester I'm teaching a class in differential equations, so we might as well talk about differential equations. You might take an ordinary differential equation, a very simple one, u prime is equal to f of u, f being some operator, say on the real line. Could be linear, doesn't have to be, could well be nonlinear. And you say, well, all right, the solution I'm looking for is probably something which is a smoothish function, so it has a certain number of derivatives. Okay, so the domain is the real line, the output is RD, Euclidean space. Okay, and so you might express this idea that I'm looking for a solution to this equation diagrammatically by drawing a very small finite category, like I've shown on the screen, whereby you imagine that the function we're after, the u is on the bottom, the object on the bottom is the solution, and then of course, when I take a derivative, that should be a morphism. That's an operation that occurs on the space of continuously differentiable functions. Of course, on the other hand, this is an equation, so really we're looking for an equalizer. Find something in that bottom object, a function that has one continuous derivative, that when I take the derivative, it's equal to what happens when I take that function, take the action of that function f. And they both should agree everywhere on the real line. That would be a solution to the differential equation. Okay, so this is great. This looks like a nice kind of description. And in a sense, this is a pre-sheaf. Awesome. Pre-sheaf valued in the category of sets for sure, even better valued in the category of continuously differentiable functions. Okay, now there's a little bit of a problem because if you recall what I had said yesterday, we're after things which are sheaves on partially ordered sets, and in that context, the base category is not a partially ordered set here. Why? Because I have two morphisms between this pair of objects. So, sort of roughly speaking, this is not a sheaf, this is a pre-sheaf. Well, okay, fine. I mean, if you want to change the Grothendieck topology, of course, then you could make it a sheaf, but that's not what I'm after here. So the question is, can we resolve this in a way that then we'll have a sheaf on a poset category, because that's the context in which the software works? Well, if you do the optimization of consistency radius that I mentioned yesterday, it will find an equalizer. But it's sort of a little hard to see that that's where it is. The global sections are not easily expressed. So let's make it a little bit more easily expressed. And it turns out this is something that comes out rather nicely in the context of how you build differential equation solutions in general. It's a standard trick. So in short, yes, although this is a sheaf in a technical sense on the appropriate site, I said I wanted to work with poset categories for concreteness. Okay. So the standard trick, this is a trick that I always like to use, and the first time I show my students this, they get a little bent out of shape, is I'm going to add an auxiliary variable. Got a differential equation, I want to solve it, add an auxiliary variable. They say, well, where did that come from? Well, in a sense, it's coming from the fact that I'm trying to pop apart this category, make it a little larger, add some more objects and morphisms, so that the resulting category is a poset category, and the structure then is a sheaf on that poset category. So a standard trick is to say, well, I'm going to add an auxiliary variable, as I said. Rather than just having u, the solution, I'm also going to carry around v, its derivative. So this can be expressed by a diagram like I've drawn. So now I have two objects in the bottom, the solution that I seek, as well as, another variation of that solution that's going to pick up that derivative. Okay, but now these two different copies of u don't agree. We've lost the fact that in the previous diagram we were after an equalizer. Here, there's no equalizer. We've destroyed that. Let's fix that by adding one more auxiliary variable, one more auxiliary object to our category. So now what I've drawn is a larger category, one that has 4 objects instead of 2, one that has 4 morphisms instead of 2. But now, if you look at this, first of all, this is a poset category. Between any 2 pair of objects, there's no more than 1 morphism. And the nice thing about this is the global sections of this sheaf are exactly the equalizers from the previous one. What have we done? Well, topologically, what we've done is we've performed an operation. We've performed a topological operation on the category. We've subdivided the category. See, in the previous category, we had 2 objects, 2 morphisms. What we've now done is we've grabbed those 2 morphisms and we've realized them as 2 objects in their own right. The original objects were still present. So if you like, the objects in the original category are now the top row of this diagram that I've drawn, and the morphisms in the original category are now the bottom 2 objects. This is a subdivision process, and you could perform this on any small category. There's a nice paper written by Del Hoyo from a few years ago that explains how you could take any small category and by providing this operation of subdivision, this is actually yields a functor between the categories. That's rather nice. And you can pull back the sheaf that we had constructed on the previous slide to this one. That's how we got this. And in fact, actually what he proves is that if you do the subdivision twice, you're guaranteed a poset category. Picks up certain kinds of feedback loops that were not present in my previous diagram. That's why I only had to subdivide once. Okay, but the nice thing is this is now something that's rather implementable in the software and has the nice feature that it's very easy to see that the global sections of this sheaf actually solve the differential equation. And additionally, as we'll see a little later on in this first hour, the consistency radius, the failure of you to get an assignment that is a global section, failure of if I place values on each of these particular objects, select a function from each of these function spaces, the failure of that to commute across the whole diagram has something to do with numerical error. And again, since I'm coming from the perspective of an applied mathematician, if I think about differential equations, the goal is really not proving existence and uniqueness. Proving existence and uniqueness is a great activity. I have engaged in this activity myself. It's quite fun. However, if you're actually working with applications, you really need the solution, but you don't need it exactly. You want a process that will approximate it. And one of the things that you'd like to know is the process of approximation going to yield a sequence that limits to the right solution, i.e. is the approximation correct in some sense? So, in fact, actually the consistency radius will help you look at and understand how these solutions interact with their approximations. Okay, but that's to come. So another perspective looking at this is by doing this subdivision, what we've done is we've kind of split up the fact that now if you look at the system of equations that I have at the top of the screen, I have how many equations? 2. How many variables? 2. So in fact, actually, if you look at it, the bottom 2 objects in this category correspond effectively to the equations, and the top 2 correspond effectively to the variables. Which is to say that the values of the variables on the left side of both of those equations are exactly the values that appear in those top 2 objects. Whereas the bottom 2 objects are a little more obscure. This is actually generally true. So if you have any system of equations, and of course, if you're an engineer or a scientist, you tend to build out equations. In fact, much to the amusement of my students, I tell them, if you pick off any book on my shelf that is an engineering book, you'll see lots of equations, because engineers like equations. If you pick off a math book, on the other hand, you'll see lots of words. Mathematicians like to talk. But this is actually a useful thing to think about, because the way that we pose our scientific models are in terms of systems of equations. And so if you perform this subdivision process systematically, with your system of equations, you can always build a nice sheaf in which the base partial order category that you're working on has effectively 2 levels. It has a bottom level in which each object corresponds to an equation, and a top level in which each object corresponds to one of the variables appearing in the equations. And the point is that you have a morphism from each equation to the variables that are involved. It's very natural. And if you look at, then, each of those morphisms, you can ask, well, what should I make those morphisms do? They should implement the equations in some sense. What you do when you place a stalk, and remember, since we're in a post-set category, these are bona fide, real, truly spaces of local sections, actual stalks, limits thereof, because we're in a finite space. The stalks on each of the variables, the top row, are in fact the sets of possible values that variable can take. Very concrete. The bottom row, on the other hand, picks up the sets of possible solutions that those equations can have. And so if you are thinking about this, this is exactly what you want if you want to solve a system of equations, and you're not entirely sure how this is going to proceed. See, if you're solving equations on a chalkboard, there's probably not too many of them, in which case the order in which you solve the equations probably doesn't matter so much. If, on the other hand, you're dealing with, say, a simulation of your entire computer system, there are probably thousands, millions, or even billions of equations to solve. And they interact in some particular way. There is a topology in play. I would imagine, and this is probably true, that if I take a look at the circuit which is in this mouse, it is in fact interacting with, by way of radio waves, the circuits in the computer, right? That's part of that whole system. But somehow the circuit in the mouse is further away from the rest of the system topologically. There's a separation there. That is reflected in the system of equations, and that's reflected in this topology as well. Okay, so if you want to see the details of how to do this explicitly, I've put a reference on the slide. You have the slides, and you can go look it up. But let's go use it. So I had a student a few years ago who was interested in macroeconomics. And one of the things that macroeconomists study is they study how the labor market works. And so they write down this system. It's called the Goodwin macroeconomic model. If you've taught ordinary differential equations before, as I have, you look at this equation, you say, that looks kind of familiar. Lotka-Volterra system, predator-prey system. I'll leave it to you to figure out whether the employers or the workers, the predator or the prey. But the idea here is I have a system of equations, got two variables in play. It's an ordinary differential equation. And if you just sit down and write down the equations and the variables, you get a diagram looking very much like the one I had in the previous slide. On the other hand, looking a little more closely, you realize the same sort of construction with auxiliary variables should be used. Okay? Because I have derivatives in play. And of course, I need to define those derivatives as well. So there's actually two more hidden equations that define the derivatives in terms of actually taking derivatives. So this then is the base partial order. The equations on the bottom, the variables on the top. Seemed kind of systematic. Let's add in the full sheaf structure, i.e., let's pass this through the appropriate functor. And these now are the stalks that sit on each of those objects, i.e., the function spaces in play, as well as the values of each of the restriction maps. What are they? Well, in some cases, they're time derivatives, the d by dt's. A few cases, they're identity maps. A few other cases, they're projection maps. And in two other instances, they are evaluate to the right side of the equation to find the left. The point of the matter is that this is a constructive algorithmic process. Give me a set of equations, I can yield this construction. Completely automated. Okay, that's rather nice. What about another system of equations? I've said circuits a whole bunch of times, yesterday and today. Let's actually look at an electric circuit. So I drew up this electric circuit. It contains 3 logic gates, each of which have a handful of transistors inside them. These are standard parts that engineers could build with. If you don't know how to read these, let me briefly explain. The little flags labeled A, B, and C are inputs. The little flag labeled D is an output. The values on the wires connecting these little yellow blobs, little yellow blobs are logic gates, the little wires carry signals. This is a digital logic circuit, so the wires can either carry a logic 0 or a logic 1, true or false. Of course, if you think about it for a moment, how could that really be? It's not that ones are moving along a wire. Electrons are doing something on those wires. So really the ones and zeros correspond to either a voltage state or a current state, depending on the technology used to build these gates. These guys here, they are low-power Schottky circuits, so they are actually current signaled. So actually the presence of a logic 1 means current is flowing through the wire, and a presence of a logic 0 indicates that it is not. So if you look at it now, we can decode this. Look at the A, B inputs. They're flowing into this little D-shaped object. That little D-shaped object is an AND gate. So if it sees two logic 1s, it produces a logic 1 on its output. Otherwise, it produces a logic 0. This guy on the end with the D output is an OR gate. So it computes a logical OR. And the triangle guy in the middle with the little circle on the end, actually the triangle is kind of irrelevant to the logic. The circle is what the engineers read as the NOT. This is a NOT gate, an inverter. So effectively what this circuit does is it takes A and B, it computes their AND, takes a NOT of it, and then ORs that with C to produce an output. So something like this. If I apply zeros on all the inputs, I'll get at the output of the NOT gate a 1. Why would I get that? Because a 0 and 0 is 0. But then 0 NOTed is 1. All right, and passing those two inputs into the OR gate, I get a 1. Of course, if I change one of the inputs, or two of the inputs, the outputs can change as well. It's worth noting, although we're not going to talk about this in detail, there's actually time delays associated with these. And those time series matter. It's also worth noting you can do various kinds of stupid tricks with these. You could take a NOT gate and wire its input back to its output. What does that do? True is false. Is true is what? Contradiction? Actually, what it turns out is that it depends on the technology that you've used to build the circuit. Some of these circuits will oscillate. Some of them will attain some value which is neither true nor false. Some of them will become unstable and will be true or false kind of randomly. Interesting. Anyway, that's an aside. The point of the matter is that this diagram that we've drawn is a representation of a system of equations, system of logical equations. Oh. You can work with logical equations just as well as any other kind of equations. This is one of the great things about category theory from a computer science perspective. Category theory is polymorphic in type. I can swap out the types instead of having to deal with function spaces as we did in the previous set of slides. Here they're just truth values. Okay, so how do I build this? Well, the same way. Each of the logic gates corresponds to an equation. A and B yields its output. That's an equation. So if I think of each of these logic gates then as an equation, that's going to be an object in my category that is going to be in the partial order, in that bottom part of the partial order with morphisms coming out of it. Each of the wires then will correspond to a variable and will correspond to the top level of the post set. I can kind of say, if I compute all of these logic values, that's great, but how do I build it? Just like this. This is a representation diagrammatically of the circuit. Oh, so what this means is I can take the circuit diagram as electrical engineers would envision it. This, as I said, I drew using a standard tool that people use to design very complex circuits. So you could just translate that net list, as it's called, directly into the diagram for a category that will then yield your sheaf. And the spaces involved, the sets that become the stalks of your sheaf, in this case, well, they're just Booleans. So what sits over the AND gate? Well, just enough information to determine what the AND gate is doing. Oh, well, two Boolean values. The two inputs will determine the output. So it's actually quite systematic. What this means then is it's actually kind of straightforward to build a sheaf that implements any kind of logic circuit. And in fact, here is the sheaf diagram then. So on the left, coming in, we have the two Boolean values, the two truth values. We take ordered pairs of them. They project back out to the inputs, and of course, they go the other direction, computing the ands. And in fact, this is something that comes up repeatedly when building these kind of models, is that the arrows that you end up building once you've subdivided do not follow the data flow. This is actually kind of, initially it's a little weird, but if you've played around with these kind of things, that starts to make sense. What we're after is we're after modeling consistency. That's what sheaves are. Sheaves are data structures to understand how local consistency works, not how data flow works. The circuit diagram had an implied direction of signal flow from the inputs to the outputs. But now this has actually got some expressive power for engineers that wasn't apparent before. And it comes from the topology. So it works sort of like this. If you imagine I'm going to feed the inputs to the outputs, that's a forward problem. That's kind of what people normally do when they're building a circuit. However, what do you do when you're debugging a circuit? What happens when your computer invariably does not do what you want it to do? Well, you have to figure out why it didn't work, right? What does that mean? Well, that means I know the output. So I actually can imagine I've placed an assignment value on the output. And I also know the inputs that I thought I provided it. But what happened in between, I don't really know. You know, what goes on inside the mind of my computer when it's not doing what I want? I know what I'm doing as input. I know what it's giving me as output. What's going on inside? If you try to extend that assignment to values on both ends into the circuit, such that the consistency radius is minimized, there'll probably be a place in that circuit where the consistency radius is sort of, that's the cause why it becomes non-zero, i.e. it's broken. So in fact, this gives us a model of not only solving forward problems, I've specified the inputs tell me what the output is, and also specifying inverse problems. I've specified the outputs tell me what inputs could have yielded it. But it also gives you the possibility of doing hybrid problems. Problems in which I know some inputs, some outputs, and I kind of want to get an inference on the inside. We'll talk a little bit more about this later. But I will say this, one of my side projects is actually restoring old computers, broken computers, for which the documentation no longer exists. It is often the case that some of the integrated circuits in the middle stop functioning. Computers have a finite lifespan. Finding that is a bit of a challenge. This gives a systematic way to identify which integrated circuit is broken. Okay, now, when I say a systematic way, then of course I should be able to give you a demonstration. So let me show you. So, once again, back onto PySheaf. I've got another notebook if you want to play with this. The link is in the slides, and you can play with this yourself. And as before, how does this work? Well, once again, once the library has been installed on the Google environment, we can import PySheaf. And a few little things of note, and this is the in-the-dirt practicality that is useful to call out. So, of course, the great thing about topoi is they tell us, hey, you can do this. And in fact, they can give us some constructive recipes, as I've shown you. But then there's some practical implications. If I actually want to minimize consistency radius to find out where that broken integrated circuit might be, I need to minimize a function. Are there optimizers that handle Boolean data? Yeah, there are some. Do they work really well? They can. Do I have access to them? Not necessarily. In the standard SciPy optimizing library that's available, open source, easy to install. In fact, we just imported it right as a, let's see here, that gets imported when you import PySheaf, it gets brought in. It's also associated with NumPy, which you see a few lines above that. It works for continuous and smooth functions. That's a bit of a problem. However, there's a nice little hack. The nice little hack is we can say, well, all right, fine, let's still do least squares optimization. The implication then is that when we go down, so here we're building the same set of building the objects in our category. When we go down and we want to add our morphisms, you will notice, okay, the inputs are in, they're fine. And is, as it says, and is times. Okay, why does that work? Well, of course, A times B, if A and B are both 1, then of course the output is 1. And of course, if the output of either of them is 0, you'll get a 0. Cool. But now this allows you to kind of smoothly move around inside there and do some optimizations. That's handy. Of course, then a not is a 1 minus. And how do you do an or? Well, you'd say plus, but actually you put a max in there because 1 plus 1 is 2, and we want it to cap off at 1. So point of the matter is, it's totally possible to encode this information in the reals such that the optimizer will be happy with it. Great. Okay, so once that's done, there's the diagram. It doesn't look quite as neat as the one that I had drawn on the slide before, but you can systematically check that this is the right one. I'm not suggesting graph isomorphism is something you want to do for fun, but it is a thing. Okay, and then we can just drop in our data values where we want. As I mentioned yesterday in answer to a question, it is a limitation of the SciPy optimizer that it wants initial conditions. What should be your initial conditions? Well, let's not bias any of the values we don't know, so we just drop 0.5s on them. And then from there on out, it's the same procedure exactly. Compute consistency radius, minimize consistency radius, and we're off to the races. And in fact, we can run that process, and what you end up finding out is that the outputs, instead of being exactly 0 or 1, can be rounded rather nicely to 0 or 1, and you can see down at the bottom, they're rather close. Now you might ask, is that close enough? I think so. Because if you go ahead and systematically rerun this code, you'll find out that it recovers the truth table, as it should. Okay, now, one word of comment here is I built this by hand, specifying each node, specifying each edge, each object and morphism in the category. Of course, I don't have to do this if I have access to the circuit netlist. If I'm handed the circuit netlist in a computer machine-readable format, of course it's very straightforward to translate that directly into the sheaf diagram with no human intervention. I've done it this way to be completely unambiguous about how it works, but it's entirely possible. And actually, if you're interested, I have another Python library that's available that will do that. Okay. So the point of the matter is that equation systems, differential equations, logic circuits, things of that sort can be encoded as sheaves in a nice systematic way. What about other equation systems? Well, one of the popular things that is useful in science are Bayesian networks, causal models. How do these work? Well, if you haven't seen them, they're kind of straightforward. They too have a diagrammatic categorial feel to them. Each of the objects correspond to random variables. So for instance, the season, or the temperature, or what choice of clothing you've made. And the morphisms get labeled with conditional probabilities. Given that the season is whatever it is, given that the season is late summer, what would we expect the temperature to be? What's the probability of certain temperatures? It's a conditional probability distribution. And of course, the same can be said for clothing. Given that the temperature is 23 degrees Celsius, for instance, what clothing choices are likely to be made? Now, if you look at this, you'll notice that the types involved are rather different. And one of the limitations of current BayesNet software is that it really doesn't like to mix types. The type season is categorical. What I mean is not so much categorical in the category theory sense, but categorical in the statistical sense, as in it takes a finite set of possible values. Summer, fall, winter, or spring. On the other hand, temperature, pretty sure that's numeric. I can read the thermometer and it tells me a number. And clothing, well, clothing is categorical as well. I can choose a short sleeve shirt or a long sleeve shirt. And I only have a finite number of them available to me in my closet at any time. Okay. So how do I translate this into an equation system and hence into a sheaf? Well, conditional probabilities, of course, are equations, right? Oh, let me also make a note here. To turn this into a full causal model, there's a notion of the do calculus. And what the do calculus does is it allows you to make an intervention. To say, well, all right, I'm going to set the temperature to be a specific value and then see what happens afterwards. This removes the dependence of clothing upon season. This is how you can do science. You do science by running controlled experiments, cutting off parts of this diagram. Effectively, science is surgery on categories. Okay, so let's try to write some equations. Of course, the definition of conditional probability is standard. There's no real surprise there. And so these two morphisms effectively look like equations. Joint probability of temperature and season is given by the equation that defines the conditional probability, and so on. But if you look at this, there's a bit of a problem. I don't really have enough equations to define clothing alone, the probability of a particular set of clothing. What are we missing? Well, if you look at this, you say, well, I don't have any way to marginalize out parts of the joint distribution. Okay, those are equations. I can write them down. Marginalization is a standard process, so I've got a handful of other equations. And if you've played around with BayesNet software, this is about as far as they typically go. And you realize that there's an algorithm to fill in the fact that this is not quite right. That algorithm is called belief propagation. What you're missing is you're missing a few other joint distributions as well, 3-way and 4-ways. I can see, but have not seen anyone write down an analogy to higher categories here. Be that as it may, this is all the equations we need for this particular system. There's a lot of words on the slide. You don't have to read them all. And it's kind of messy, so let me summarize it a little bit. Let me call the variables x1, x2, x3 just to keep things a little bit cleaner. And you'll see that there's two kinds of equations in play. There's the definition of the conditional distribution, of which there are two. And then there's 9 equations that define marginal distributions. All right, fine. In terms of what we do next, well, now we have a system of equations that define the full setting we're interested in. Okay. What are the spaces involved? Well, the spaces are probability distributions, or rather, the spaces are spaces of probability distributions, spaces of signed measures. So the M's indicate signed measures. So if you take a look at the first equation, the equation that defines the joint probability of x1 and x2, how does this work? Well, it takes a single variable distribution, a distribution for x1 alone, and translates it into a joint, a distribution for x1 and x2 jointly. The conditionals, if you will, go from a small number of variables to a higher number of variables. Marginals go the other way. Take a large number of variables and remove some of them from consideration. So some of them go up in size and some of them go down in size. Okay? This is an interesting fact that helps organize how you build a sheaf. Again, this is an equation system, so it will have 2 levels. The bottom level will correspond to each of the equations. The top level will correspond to each of the variables. And you can see there are, for instance, all of the variables in play and all of some of the marginals. Yeah, they're always there. Here are additionally the conditionals. This gives us our BayesNet structure. So the distinction here between the blue arrows and the black ones is the blue ones are specific to the BayesNet itself. The black ones are there whenever you have 3 variables in play. So there's actually a marginalization sub-sheaf that's present. Incidentally, marginalization and applying conditionals are both linear operations. So this is actually a sheaf that's valued in a category of more algebraic things, vector spaces. As such, I can compute cohomology, should I wish to, and I can tell you that the marginalization sheaf actually is acyclic. It does not have interesting cohomology. The only way you get interesting cohomology, and you can get interesting cohomology, is by adding the Bayes net structure. Something of an aside at the moment. But here's the point. I've got my Bayes net. I can now notice that if I go ahead and try to solve for find me the global sections, that's literally just finding consistent sets of distributions for each of these random variables. So now I can say, all right, I've got this consistent set of distributions. I can play the same kind of games that I wanted to play with the digital circuits. I can play a forward problem, say I know what x1 is, let me try to find what x2 and x3 are. How does that work? I place an assignment on the top mx1. That's the distribution of x1. I know what it is. So I select a distribution, I place it there in the sheaf. And then what do? Do I know the others? No, I don't really know any of the others. So what then I do is I just say, let me minimize consistency radius. And when you minimize consistency radius over that particular sheaf with that particular assignment starting out at the upper left corner, that literally is the algorithm that's known in the Bayes net community as belief propagation. But I can do other things that are not belief propagation. I can say, suppose I know what x2 is. That's in the middle. That's neither a forward problem nor an inverse problem. From the perspective of the sheaf, it's no different. You place an assignment, you minimize consistency radius. Suppose for a moment I happen to have access to one of the joint probabilities. It's the same story. Well, that's really kind of interesting. And of course, I mentioned a moment ago that the do calculus is in play. If I want to perform a controlled experiment, I intervene and tell you what the value of x2 is because I've decoupled that value. I've forced it so it's no longer governed by x1. That's a surgery on the topology. What does that mean? Well, that means that you end up removing the arrow that I've marked in red. And then you place your assignment at x2 and go from there the same way. So the point of the matter is, causal models can be manipulated very easily using this framework. You have a very flexible framework for manipulating and controlling them. Again, you don't want to build these by hand. That's why there's this other library that I mentioned. So you can take these kind of systematic models used in science. These are especially important in epidemiology. Because you say, I don't know what causes what exactly, but I'm going to posit this Bayes net construction. And then I'm going to say, well, I can perform some controlled experiments, but not others. And I can then infer missing information. Okay. Now, I want to end with, the next 20 minutes or so, explaining some things about differential equations. Now, when you talk to people who solve differential equations using numerical techniques, there's often a discussion about how you discretize the problem. If I start out with a differential equation that I'd like to solve, you can try to solve it directly, but there's only a handful of equations that we know solutions for. This is the sort of thing that if you're, say, for instance, in a partial differential equations class, you'll learn, we know about the heat equation, we know about Laplace's equation, the wave equation, transport equation. Any others? Not really. Why not? Well, aside from the fact that we tend to run out of time in the semester to do more than that, those are really the only ones that we can write down a solution for explicitly relatively easily. If you move over to ordinary differential equations, there's a handful of ordinary differential equations we know how to solve exactly. All the others we have to approximate. So the business of numerical analysis is to say, I have a differential equation, some infinite dimensional thing, and I'd like to approximate it with a finite dimensional approximation. How do I do this? The recognition is that there's effectively two ways that you might do this. You might either discretize the domain. I'm solving a differential equation that has x as an independent variable. I'm going to look at finitely many x, or perhaps a countable number of x. Find the values of the function that I'd like to solve for on those values of x. and then render the differential equation into a difference equation. Interesting historical point. This is why the first computer design occurred. This was not an electronic computer. This was a mechanical computer. This is what Charles Babbage was after, was he built a machine to solve difference equations. Now, that's one side. You could discretize the domain. You could also discretize the codomain. And this is a little more subtle, but instead you say, instead of the solution being discretized in X, you're going to say the solution is a sum of a bunch of functions that I know. Sum of sines and cosines, perhaps. This is how you get Fourier series solutions, which is a standard way of solving, say, the heat equation. Oh, okay. So we have these two. How are they related? Well, I'd like to show you. So, for instance, if I have a k times differentiable function, discretizing its domain amounts to a function that takes as input that k times differentiable function f and yields a sequence of samples, values of f at certain fixed x values. Okay? On the other hand, discretizing by way of discretizing the codomain involves rendering that function into a sum of known functions. Now, of course, especially if you're a physicist, it's very common to think that these two things are basically the same. The guy the guy that I've shown here on the left side of the screen, you could think of being a sum of Dirac delta functions to yield to the other one. I think it's useful not to do that because there's actually a directionality to the arrows that I've just drawn, and it kind of plays with that. So I've got these two kinds of discretizations. As I said, why would you want to do this? Because there's a differential operator you'd like to work with. That differential operator consumes some of the differentiability, so you could discretize as well. So now I have two different discretizations, one before and after taking my differential operator. Okay, now if that's a differential operator, that's kind of hard to work with. When I render a differential operator into a difference equation, that's really happening on the left side. When I render my differential operator into something acting on basis functions, that's on the right side. So effectively what I'm typically after is asking whether or not these two sides of the diagram commute. On this side is finite element approximation, sum of basis functions being used as a proxy for solving the differential equation. Whereas on the right, it's a finite difference approximation, using values of the function and taking differences of them. And the goals in either case is to make the diagram commute as best you can. You won't be able to do it. You can't be able to do it, except if your function, your differential operator, is a line, doesn't take any derivatives. Because effectively, on this side here, we're talking about Taylor series, and on that side there, we're talking about interpolation. Okay, so let's dig into this a little bit. Let's take the original example that I started this discussion with. Consider this differential equation, u prime equals f of u. Single first-order nonlinear differential equation should not be that hard. This is the sheaf diagram that we had drawn for that. So as before, you'll notice that the u prime variable is in the upper left corner. You want to find then, okay, I want to solve this differential equation. If I want to solve this by way of a finite difference approximation, what that means is I'm going to take each of these function spaces and sample them by way of specifying specific x values and evaluating the function in that function space on those x values. So as such, this yields a bunch of sampling functions. So on this side is the continuous model, and on this side is the discretized model. Here, just for kind of clarity of discussion, I've assumed that we've got an infinite grid with even spacing. As is traditional, we call it the step size, the space between sample points h. And what you end up with is a model of this differential equation that kind of is based on conflating the difference between taking derivatives and taking difference quotients. Okay, all right. Well, if you look at this for a moment, you say, well, this guy's a sheaf on this side, because that's how we built it. And if you look at the diagram over here, does this diagram commute? Yeah, it should commute as well. So this guy here, too, also is a sheaf. These dotted lines then look very suspiciously like a natural transformation. A sheaf morphism in the category of sheaves. Well, let's check. Let's see, is this really a natural transformation or not? How do you do that? Nothing to it but to check commutativity. So let's do that. So, we want to know, is this a sheaf morphism? Does this diagram commute? Well, if you're careful about making sure that the actual differential equation function f that we're trying to solve for shows up on the other side here, the green square that I've shown commutes. So this can be constructed so that this works. Okay? There are various strategies for this. If you're interested in this sort of thing, this is the business of numerical analysis. Okay, this one commutes without incident. It's trivial. Just outright everyone is fine. So does this one. Again, no issues here. All right, because all I'm doing here is I'm taking a difference and checking and matching it up, taking a difference, matching it up. Of course, that commutes. There's no work. This one, on the other hand, that was a problem. Because what's going on here, let's follow it. I'm taking a derivative of a function here and sampling it, and comparing that to what happens when I sample the function and take a difference quotient. This is exactly the point of saying that I want to ask for my function to have a derivative which is exactly equal to its difference quotient, i.e., function is equal to a one-term Taylor series or two-term Taylor series. Yeah, that doesn't happen unless my function is a line. So that's not going to work exactly. So that means, as a result, this diagram is not a natural transformation, but it's close. It's close to a natural transformation. Additionally, we know that the category of sheaves is a topos. So we have exponential objects, yes? This natural transformation that not quite natural transformation that we tried to draw here, really then wants to be an object in my category as well. In fact, this then is a pre-sheaf, not on my category of posets, but it is yet a pre-sheaf in the category of sheaves that I've drawn here. So I can ask, if I lay down data, what is the consistency radius? I.e., I can ask, how good of an approximation is this? The failure to commute is an indication of the kind of error you pick up when you use this difference approximation. Of course, we can go the other way. We can use the finite difference approximation idea, but parry it over, dualize it, into a finite element approximation. So I've picked up our continuous sheaf model, put it on the other side, because instead of being pushed forward, this is more of a pullback kind of construction. If I build a finite element approximation, what am I doing? I'm building the values of the function space by way of making a sum of basis functions. So on this side now, I have a new sheaf model that approximates my original one. So again, the same question. Is this a natural transformation? And of course, you could probably guess that things may be not so good, but let's check. This one's fine. There's no issues here. Be careful about how you choose things, but you'll be fine. The problem comes, as before, when we try to say that our function is exactly the sum of our basis functions, which in general it's not. However, interestingly enough, the story is a little different here. See, if I have a differential equation, I might actually be able to solve for certain basis functions and find that they are actually showing up as solutions. So, for instance, if I have a second-order linear differential equation, it might well be that I know how to access those basis functions. Second-order linear differential equations have not lots of nice properties. And for instance, I might know, hey, there's sines and cosines, and those are exactly solutions, except that they're not satisfying the boundary conditions. This is exactly what the Galerkin methods do. Galerkin methods will build up your basis functions using bits of solutions, in which case this actually does commute, in which case actually you do get a natural transformation. So the important point here is there's actually a category theoretic reason why you might prefer to use a Galerkin method rather than a finite difference method, is because it forces this diagram to turn into a natural transformation. Once this diagram's a natural transformation, then it's game on. Then you can take this new whole diagram as the diagram of a fresh new sheaf, of course, because we have exponential objects. So then I can start to say, well, all right, great, I'm going to solve on this side of the world. Minimize consistency radius starting over here and propagate the whole thing through. This is, in fact, a representation of what Galerkin methods do. So observations then are coming back to this construction. In general, when you're solving nonlinear differential equations, usually you're either discretizing the domain or the codomain. And in general, you don't end up with commutativity. But in the case of certain linear differential equations, part of the reason why linear differential equations are tractable is because, in fact, you end up really getting a natural transformation, morphism in the category of sheaves for them. And then things are much better. So let me end this session right now in summary by calling out a few things to kind of highlight where we've come. We started out with the idea that we could build sheaf models of systems, and I gave you some examples yesterday. But now we know any system of equations can be written systematically as a sheaf. These include systems of differential equations, which show up all over the place. They include things like logic circuits. They include Bayes nets, causal models, basically anything that you can describe by equations. Now, let me make an observation here. This is, in some sense, not new theory exactly, because we know that we can encode logical systems, things which are in first-order logic as sheaves in some way. So, of course, all of that kind of fits here already. But these kind of constructions are tractable, and we can write them on a computer. Once we've done that, we're in a situation now where we can start to quantify measurement error. How big is the consistency radius? We can optimize consistency radius to solve certain kinds of problems that look like either forward problems, inverse problems, or anything in between. And from an applied mathematics standpoint, that's really super valuable. Applied mathematicians have long solved forward problems and inverse problems, but they really haven't been in a position to address the anything in between. And of course, that's what science is about. And finally, the fact that some of these models may be approximate due to modeling error or discretization error, such as what occurs in solving differential equations in practice, all of these can be addressed within this framework. And I think that's extremely valuable. So I'll end there, and we'll pick up after a break. So let's wrap this up. We've now seen several different ways to build some sheaf models systematically. We've heard about how you can infer missing data or clean up some noisy data or handle forward inverse problems, inverse problems, and everything in between. But now what about the domain of validity of each of these parts, i.e., what about the topology? Because I noted on my first slide, and there's a reference to the first slide, saying that the point is that sheaves allow you to moderate between different levels of abstraction. And when you think about it for a moment, if you take the logic circuits example that I gave you in the last hour, and you imagine extending this to billions of gates, it's going to be kind of a mess. So the question is there a systematic way to find what the right topology is to work with? This is related to the questions of saying, I have a collection of models that I want to find the topology that's making them all consistent. That's very similar to what Laurent was telling us yesterday. But the question is, in some sense, can I find a topology on which there is consistency across the board? Now, I have to be careful, because my sheaves are not valued in set, they're valued in metric spaces. So what this means is there is a certain amount of error. If I have a very, very tight tolerance, I want a very small amount of error. What this will tend to mean is that if I look for open sets in my topology, roughly speaking, that are consistent to that tolerance, I won't find very many. Which is to say that the topology will end up being, at best, very fine. Lots of open sets. On the other hand, if I'm more tolerant, I accept a larger consistency radius, more of this overall diagram, more of the base category, will have a part of the sheaf that is consistent to that level. And of course, if I'm fully tolerant, happy to consume just about anything, then of course, then we're back in pre-sheaf land. So it seems that once we've built a sheaf on a metric space, there's some freedom in choosing how much tolerance we want. And of course, I had started the discussion yesterday by saying engineers, when they build systems, build them to tolerances. And those tolerances have legal, financial thresholds that get triggered. If you deliver a system that violates one of your design requirements, that has consequences. So the point of the matter is we'd like to understand how this works and use this information to find sort of a natural topology, not just for a sheaf, but for a sheaf and an assignment simultaneously. So the distinction here is, and as always for me, I'm not dealing with a whole collection of sheaves, typically. I'm dealing with one, or maybe a handful. But I'm also dealing with assignments on them. I'm dealing with the data as well. And so the point is, I want to understand what the right topology is that pairs up the data and the model, the assignment and the sheaf, to a specified but variable level of accuracy. Okay, now that seems fairly abstract and high-level goal. Let's be a little bit more specific. So, for instance, I did a project a few years ago where we were looking at astronomy. We were looking at star clusters. We were looking at cameras that were taking pictures of star clusters with a very small number of pixels. And the question was, how accurately can you count the number of stars in those star clusters? Because those have implications for understanding the age and the history of those particular star clusters. So, for instance, if you see a star cluster like this is a fairly bright one. You can see this with a small telescope, and you can count the stars very easily. But if it's fairly dim, or you take a picture of it, you have a number of pixels. Well, you say, well, how do I count the number of stars? Well, you want to find the bright pixels, I guess. But that doesn't quite work, because what if you have a star that's kind of large? It takes up more than one pixel. Counting the bright pixels doesn't work exactly. Maybe you want to find the local maxima of pixels. That works a little better, but not particularly great. There's a whole literature on star counting, as it were. A whole collection of algorithms, some of which are linear, some of which are nonlinear, for doing this. And as it turns out, they all are kind of weak, in a sense. They all kind of have a problem. And the issue is that if you're trying to count the number of stars, you're also trying to find where the stars are located. You're doing this simultaneously. So the right strategy, in some sense, is to say, well, I don't know the number of stars. And I have a nested sequence of models. I have a model that says, suppose there is one star and it is located here with a certain brightness. So if you say the position and brightness is given by a set I, has a little bit more structure, it's a metric space. I can say that if I have p stars, well, the order in which I list them doesn't matter, so I quotient by the action of a symmetric group of p elements. That's reasonable enough. So the data space, if you will, the variables in play, are described by this position and brightness space quotient by the action of the symmetric group. Okay? And the thing is, I don't know how many stars there are. So either P is 1, there's 1 star. P is 2, there's 2 stars. 3, 4, 10,000, I don't know. But if you notice, the models should be nested. The model for 1 star, somehow that information, if I have 2 stars, is kind of included. Or you could go the other way. You could say, if I have the model of 2 stars, I could project out to get 1 star. The inclusions work a little better as it happens. And although this is the same kind of partial order structure I'd drawn on the previous slide, it's upside down. Don't let that bother you. The variables that we're trying to predict are the number are based on the pixels, and it's actually valued in the natural numbers. Why natural numbers? Important to know the data. The data are actually the number of photons that have arrived at each of the m pixels. So the data you get actually are categorical, they're discrete. Okay, fine. So the point is now that I have a nested sequence of models. Sequence of models in which I have 1 star, or maybe 2, or maybe n. I don't know how many. All of them attempt to predict the same distribution of photons across pixels. Now here's the intuition. The intuition is that these models being nested correspond to a nested sequence of subsheaves, one inside the other. I can compute the consistency radius for each of them. And sort of the intuition is if I overshoot the number of stars, if I have position and brightness available to me, if I have too many stars, well, what will end up happening? Well, I'll end up with maybe the model will say, hey, there's a star of brightness 1/2 here and another star of brightness 1/2 right here. They both sum up to a star of brightness 1. You'll get some ambiguity. However, you'll be able to match the data pretty well. So what this means is as you propose more and more stars, the consistency radius associated to that particular subsheaf will decrease until it sort of drops precipitously down to a small value, basically amounting to the measurement error in the sensor, and stay there from there on out. So in fact, what you really want to do is you want to look for a knee in the curve. Find the place where the consistency radius drops down to 0, and it actually does so fairly precipitously, kind of like falling off a cliff. And from there on out, for more stars, that consistency radius is small. So in fact, this is how you can count the number of stars, and as a consequence, you also know where the stars are, which is kind of useful. It turns out when we ran this approach actually did better than all the state-of-the-art algorithms, which was kind of surprising to me, because I figured I'm just sort of playing around with this theoretically, but it actually works better. There's a paper if you're interested in reading this. So now what are we doing really when we're nesting subsheaves inside the other and computing their consistency radius? Well, we're building the consistency radius, and as I had said before, this is kind of a recap in a sense, the consistency radius is somehow a lower bound on the amount of error in your system. Lower bound on the distance to the nearest global section. Okay? But now if I take an assignment, so here's an assignment, and I grab a subsheaf, which I've highlighted there, and I ask, what's the consistency radius on that subsheaf? Okay? It's a particular value, in this case happens to be 0. Turns out that as I expand out, go from a small subsheaf to a larger one, go from a small open set on which my sheaf is defined to a larger one. Imagine including my subsheaves into the larger one by way of topological inclusion on the base space. The consistency radius is monotonic. Well, you can see that from this example. If I make the set bigger, take a larger subsheaf, the consistency radius goes up. It was 0, and now it's a larger number, 2 square root of 14 in this case, I guess. Oh, Well, whenever you have some kind of monotonicity condition like this, you can play with this and use it to yield a better invariant. Oh, well, let's look at this very, very closely then. So I've taken a very, very small sheaf on a very small poset. The values are real numbers, just for concreteness. The quantities in parentheses are meant to be interpreted as linear maps, i.e. 1-by-1 matrices. So multiply a number by 1, that's the identity map on that side, and on the other side, multiply by 1/2. Okay? So what happens if I place down an assignment on two values? Say I got an assignment on these two different objects here, and I want to find what value should I place on that red question mark to minimize consistency radius. Okay, well, since the value here is 0, 0 times 1/2 is still 0, effectively the influence, the residual from the left side is saying try to make that value as close to 0 as possible. Of course, on this side here, 1 times 1, last I checked, was 1, and so that's saying make the value as close to 1 as possible. Fair enough. All right. So what this is saying is I'm trying to balance between 0 and 1. If I use the Euclidean distance, obviously I have to pick a half. This is the assignment that minimizes the consistency radius. Okay. Now what happens if I want to find the global section? The nearest global section, however, because the 1/2 and 1 are not symmetric physically in this diagram, the nearest global section is not to place a 1/2 in the middle. The nearest global section ends up placing you 2/3 and 1/3, and consequently 1/3 in the middle. This is in fact a global section. This is easily checked. Everything is consistent, right? 1/3 times 1 is 1/3. 2/3 times 1/2 is 1/3, so that all checks out. This is a global section. And as it turns out, this one is the closest to the original assignment that I laid out. This is closest to these values. But it's not the same as what you get by minimizing consistency radius. They're different somehow. Well, that's kind of interesting. Now, if I extend out to a larger sheaf, i.e. fill out the space of open sets, or the category of open sets, compute a limit, fill in that bottom. This is now all of the restriction maps amongst all of the open sets. All right. We play the same story, 0 and 1 as before. If I go ahead and extend to the minimized consistency radius, well, what ends up happening on the bottom is, in fact, you find the nearest global section, the 1/3 that's there. That 1/3, if you multiply on one side, you get the 1/3 of the nearest global section. On the other side, you get the 2/3 of the nearest global section. If you're using the Euclidean distance, interestingly enough, the value in the middle ends up being a little ambiguous. It can be any value between 1/3 and 2/3. 1/2, as we had found previously, is in fact between those two values. That's consistent. So that's kind of interesting. Now, why am I telling you this? Well, this is now a good place to start to ask the question about how this monotonicity of a localized consistency radius works. Okay, so let's do that. What's the consistency radius on this open set here? Well, it's just 1/2. The distance between 0 and 1/2 is 1/2. Likewise, on this side, the distance between 1 and 1/2 is also 1/2. Okay, fair enough. What about the consistency radius on the top? Well, there's nothing to compare it with, so that's trivially 0. Okay. Now, what about the whole thing? Well, the whole thing, the consistency radius is just the consistency radius of the whole thing. So checking all of the different possible combinations, they're all actually shown here, is 2/3. And interestingly enough, at this point, it starts to look like you might have a measure. Take the open set on the left, open set on the right, add them up, subtract the intersection. Since the bottom one corresponds to the whole thing, it would feel like that ought to be equal, but it turns out it's not. The consistency radius is merely a bound. This is what is called an inner measure. So, as I state here in words, the local consistency radius of a global assignment is a loose upper bound for the global consistency of a local assignment. These two words, global and local, don't quite commute. So this suggests then that if we want to use this filtration to find out what open sets should be in play at a given tolerance, there's going to be some care needed. And that's true. So I'm going to start out by showing you an example of a situation in which we can compute this local consistency radius, and we're going to use this as a running example. This running example actually, reconnect please. All right. This running example makes use of several other features I want to call out. So as before, we start out by loading up the library. And this example here is an example of taking a US East Coast road trip. And I want to know how much distance accumulates over the course of my road trip. And the way that this works is, as I'm driving, I go between different cities to stop, and there are certain choices that I can make. The names of the cities are not that important for our discussion right now, but you can see the ones that are involved are listed here. So we start out in Nova Scotia, and we could potentially end in Miami or some subset. This example shows a subset, just to keep the graphics from getting out of hand. But the point is that we've tabulated the distances between all of these cities. And that's written here. Of course, you could have loaded this from some kind of mapping file. But all of this data is present. This is useful. This is, in fact, a graph, an adjacency list. And so I want to show you systematically now. I've mentioned a few times you can build a sheaf systematically by way of software. Now I'm going to show you how that works. So the basic idea is we take our adjacency list, we pick out which cities we'd like to visit, and we can build. So how does this work? Well, once again, we import PySheaf, start by, as before, assembling our sheaf and saying, I want to give me an empty sheaf. Let's use Euclidean distance as before. And now, actually, it's very easy. We take our adjacency list, so one of these lists that was present above, and we can just simply systematically loop over and build each of the objects in the associated category. What are the objects? Cities. Okay. What are the morphisms? Well, the morphisms have got to be the connections between the cities. Drive from city A to city B. From city B to city C, and so on. Each of those are the morphisms. In the sheaf, what should the action of the sheaf on those morphisms be? Well, when I drive from one city to another, I'm keeping a running tally of how long it's taken. So the values on the objects is the current time, or how much time has been consumed by driving. And the restriction maps then are simply adding on bits of time. And in fact, you can see that what we do, well, it's an anonymous function, a lambda, that takes as input the current time and adds on the time that it takes to make that particular transit. How does it find that particular time? It looks up into the table. So this gives you an idea that systematically, when you want to build these sheaves out of a data structure, the process of making effectively a sheaf compiler is part of how we build sheaves in practice. It's to take our data structure that's been given to us by someone else. In this case here, it was a graph structure, but certainly could be a circuit netlist, could be a specification of a grid for a numerical solver, and assemble systematically the objects and morphisms. Now, one of the things that you will notice when you start to look at this kind of data structure is that driving from one city to another and from another city to another turns out not quite to satisfy the triangle inequality for various reasons, some of which is that the data are accumulated empirically and traffic is totally a thing. You get stuck in traffic on one path versus not another at different times, and depending on when those data were collected, you don't end up with a diagram that commutes. So in fact, at the end of this construction, we don't actually end up with a sheaf. We end up with just a pre-sheaf. Okay? Now, in the previous hour, I had mentioned a means of subdividing to turn my pre-sheaf into a sheaf. But I'd also said that from the standpoint of the software, we don't necessarily need to. So now I want to kind of call that out a bit. When we're building an assignment on a pre-sheaf, and then you minimize consistency radius, what are you trying to do? You're trying to make it such that when you take a value on a particular object in your category and you move it around by way of following the morphisms to any other place in any other object in your category, you get the value that's already there. That's what you're trying to assure. And when you minimize consistency radius, you're doing so by saying, I'm going to move around the data values such that they get as close as possible. What this means is you are automatically finding equalizers. You are automatically enforcing the sheaf gluing axiom. And so what you are automatically doing is finding a single part of, a single element of a sheaf that is the sheafification of your pre-sheaf. But I want to emphasize that while, as mathematicians, we're very comfortable sheafifying things, right? There's a nice adjoint, yield the sheafification functor, we're done. Computationally, that's expensive. You don't want to do this unless you have to. So the strategy here is we're going to only run that sheafification functor on this pre-sheaf when we have to for specific values for a specific assignment, lest you incur a lot of computational cost. Now, in the case of the previous talk, that was the motivation for why I used the subdivision, introduced auxiliary variables to yield a sheaf on a poset. That way the reasoning, the interpretation is a little clearer. Whereas here, the computation is what we're after. Okay, so if we go ahead and do this, we can verify, all right, there's our path, and you can see that there aren't that many choices on part of the path. This is Nova Scotia. I think this is Bangor, Maine. There's not that many main roads if you want to get from one city to another in the most northeast corner of the country. Things get a lot more complicated when you start running into Boston and Providence, New York City, and such. There's a lot more options there. This is the place where the diagram gets a little bit more complicated to draw, and it's also the place where the resulting functor is a pre-sheaf and not a sheaf. Okay, fair enough. So now I mentioned that we want to understand how much error gets accumulated. And here's an interesting thing. If I want to go ahead and compute how much error is accumulated as I'm moving, effectively that error is going to increase when I cross over certain points as I move along my path. And I can see that by way of computing the local consistency radius. Okay, so the story then is much the same as before. We're going to run our consistency radius minimization process here. There's a bunch of setup code before that. And when we do that, we find, all right, consistency radius looks like 3 hours, roughly, amount of error differential between our various paths. Fine. But now I want to understand where is the biggest accumulation of error. Okay? I do that by way of finding the local consistency radius. And in fact, there's a single function that will do that for you in PySheaf. Say, I'm interested in, actually there's two of them. One function that says, I want to find the local consistency radius on a particular open set, and so you specify the objects that you're interested in. There's a faster version, the star local consistency radius, that applies to a single object. To say, I want to know the contribution of this one. And so if we run that, you can end up seeing this. These are the various contributions, the local consistency radii associated to each of the nodes in this diagram. Worth noting, this was computed while we were sitting right here. It's efficient. So the point of the matter is we can start out with a sheaf diagram or a pre-sheaf diagram. If you're not interested in reasoning about it logically, but you want to do computations with specific assignments, pre-sheaves are quite sufficient. And once you have a pre-sheaf, however, then looking at the local consistency radius is meaningful. Okay. So let's now dig into this a little more. So the consistency radius, as it happens, as I've mentioned, allows you to identify open sets on which there is consistency. So if I start out with a very, very stringent tolerance, say, tell me all of the open sets that are consistent to a value of 0. That says, find me all the places where I have an actual section, which is to say that the assignment is consistent with itself when I move around values all over the category. Well, in this particular example, there's exactly one open set that has that property. Why, in this particular example, there's only one place where there's nothing to compare. Sort of pathetic, but so it is. Now, if I ask the same question for, say, find me all the open sets that are consistent to 1/4, well, there aren't any that are consistent exactly to 1/4, and the 1/4 or below picks up the same one. So things are much the same until we get an abrupt shift at 1/2. At 1/2, find me all the open sets that are consistent to 1/2. There are 2 of these that have not already been accounted for. Those 2 that are now present, I show here, the left and right sides of that particular diagram there. So there are now 3 open sets that are consistent to 1/2, 2 that are exactly at 1/2 and 1 that's at 0. Okay. Well, then you could say, all right, let me dial that up a little bit. Nothing happens until I finally hit 2/3. 2/3 is where I've hit the full consistency radius of the whole thing, the global consistency radius, if you will. And from there on out, nothing else happens. Now, because of monotonicity, every open set that I had at a lower consistency radius value is going to remain consistent as you increase the threshold. So every open set here is a subset of one of the ones that follows. So what this means from a computational standpoint is once you've seen an open set, you know it's around from there on out. So you only really need to know the point at which that open set occurs. The smallest consistency radius for which the data are consistent on that open set. An additional point then is that we're building a progressively larger cover of my space. And by the end, you've filled out a specific cover of the entire space. I suggest to you that this is actually the natural topology for this data, not the one that we had specified originally. This topology that we found, the one that is associated not just with the sheaf, but also with its assignment, is the one that you want to think about. So when you build a system that may be built out of this variables and equation structure, you end up with a very fine topology, lots of open sets. Many of those small open sets are effectively too small. They're capturing details you don't care about. They're not at the right level of abstraction associated to the data you're working with. But from the standpoint of the sheaf, you can't tell that. But once you add some data, once you've added some data, now you have a sheaf and an assignment. Then you can answer the question, which open sets at which thresholds are the ones that we should be looking at? Oh, okay. So which open sets should we be looking at as we vary the thresholds? That turns out to be the right thing to think about. And from the standpoint of building this construction, the thing to recognize is that when I go from one threshold to a higher one, since I have monotonicity, the covers only get bigger. So this cover necessarily covers that one, this cover necessarily covers that one, and so on. And in particular, you have refinements of covers. One open set sits inside another cover element by monotonicity. Turns out, this thing is a sheaf on a topological space in its own right. It's a sheaf of coverings. There's a category of coverings in which the morphisms are cover coarsenings or refinements, depending on which way you want to go. contravariant or covariant, doesn't really matter. This is a sheaf on the real line. So that's kind of neat. That's kind of useful. Of course, then the question is, can you compute this? Can you compute this efficiently? And the answer, of course, is yes, you can. And in fact, it's actually it's a single call. So if you call for this consistency filtration, you specify which threshold values you'd like to examine. So in this particular case here, I've examined, looks like 200 thresholds between 0 and 3. How did I pick 3? Well, that was the global consistency radius. So if you select 200 thresholds between 0 and 3, it samples, sweeps through all of those thresholds, accumulates the cover elements, and then gives them to you. So it says that there's one cover element here between these two thresholds, so between 0.015 and 0.3 in this particular case. There is only one open set which is consistent. It's that open set containing, looks like Providence, Rhode Island. As you dial the threshold up a little bit, up to 0.15, we get another cover element materializes that picks up Providence and Worcester. Of course, the previous open set is still there. It doesn't need to be listed. That would be redundant. No need to redo that calculation. Now, you might ask, why are the edges not matching up exactly? There's a little bit of round-off error in play. But the point of the matter is this is something you can do efficiently, and the reason why it's efficient is because of the monotonicity. Okay. Now, that's useful. It is a sheaf on its own right, this consistency filtration. The coverings that you yield are the natural topology to work with for your data and model paired. It's a natural question, is this functorial? And the reason why I say this is a natural question is because the consistency radius itself is not functorial. If you take a sheaf and you map it through a sheaf morphism, you take the assignment, map that assignment through the sheaf morphism as well. Of course, the data gets dragged along for the ride. I can compute the consistency radius on both the domain and codomain of this sheaf morphism, and there's not much of a relationship between those two consistency radii. It's not functorial. However, this consistency filtration is functorial. And in some sense, this explains the reason why. The reason why consistency radius is not functorial is because there are various cover elements that come and go, and they might appear abruptly. But interestingly enough, not only is this functorial, it's also continuous itself. Remember, the consistency radius is continuous. If I vary the assignment by a small amount, or I vary the sheaf by a small amount in the appropriate topology, the consistency radius varies by a similar small amount. That's why minimizing consistency radius is a reasonable thing to do. But it turns out this consistency filtration, which is this somewhat elaborate sheaf of covers on the real line, it is not only functorial, but it also is continuous. It's not continuous in a reasonable way, though, or at least not no, take that back. It is continuous in a reasonable way, but it's a little subtle. It's continuous in what's called the interleaving distance. So what this amounts to doing, how do you compare two coverings, or rather two consistency filtrations? The way you compare coverings is you ask, do they refine each other? If I have a cover that refines another one, and that other cover refines the first, they're somehow equivalent. Refinements being morphisms in the category of covers. So you can ask the question, is it possible to take this filtration, so the function from 0 to infinity that tells you which covers are in play at which points, and compare the covers associated with them to a similar such structure? And the point of the matter is that they're probably not related at all, it seems, unless you perform a transformation of the domain. Why is this? Another nasty fact about reality. The nasty fact about reality is that when we make measurements of things, they come with units. Units matter. So for instance, if you want to measure temperature, measure it in Celsius, measure it in Kelvin, measure it in Fahrenheit. If you want to be really abstruse, measure it in Rankine, right? But these are all the same thing, are they not? They're really all the same temperature. When I store data in a sheaf, that's storing data in the assignment, that's storing data in the values, and the metrics are sensitive to the values, which read out in units. That means the consistency radius measures out in some sort of units. And they may be weird units because they may be kind of amalgamated units from different data that you have floating around in your sheaf. And so if I want to compare with another sheaf and its assignment and its consistency filtration, I may have to perform a units transformation on the consistency radius threshold. So the point of the matter is that these two consistency filtrations, if I want to compare them, I first transform that threshold, and then I ask, do the covers under that transformation refine each other? And then I ask, how far did I have to move them apart around inconsistency values so that they do refine each other, if at all? The minimum of that distance is the metric in play. So I want to show you how that works. So suppose I have these two different sheaves paired with assignments. The comparisons always must be sheaves paired with assignments, models with data. We're no longer purely in the category of sheaves alone. We're in the category of sheaves paired with assignments. So I have a sheaf assignment on the left and the right. If you look at them numerically, they're not too far apart. The assignments aren't too far apart, and the restriction maps are not too far apart. You're allowed to perturb both of them. I want to show you. I've computed for you their consistency filtrations. This consistency filtration is rather symmetric. Why? Well, because the sheaf is rather symmetric. This one here, since I perturbed it, so I started with that one and modified to get that one, you'll notice that, okay, the scales, the vertical scales don't really matter because that's not a distance, but the horizontal scales are consistency radius scales, and they're a little different. But you can kind of see that they both kind of schematically look the same. Homotopy equivalent as it happens. That's spurious. It starts out with one cover element, just C. That's the guy on the very top. There's nothing to compare with, so that's perfectly consistent in both cases. At some point, I've got enough threshold to pick up one of the left or right sides, which you can see. This one, they both show up at the same point. This is the example we had been looking at previously, where both of the open sets at the top had consistency radius 1/2. Whereas over here, they don't come in at exactly the same. This one comes in at 1/3, and the other one comes in at 0.3, and the other one comes up 0.6. So the point of the matter, though, is that if you squint your eyes, these look very similar, and that's sort of the point. The point is, if I deform the horizontal axes a little bit, I can kind of mostly sort of align these, and then do a little additional adjustment. That a little adjustment I'm measuring to make the metric. That tells me how far apart these are. Okay. So the point of the matter is this consistency filtration is continuous in the data. That means it is meaningful and useful for performing optimizations and robust to noise. So it's a useful geometric invariant. Now what about functoriality? I claim this thing as a functor. But now I have to tell you how morphisms in the category of sheaves paired with assignments, not just category of sheaves, but sheaves paired with assignments work. They should be some kind of natural transformation. I mean, the morphisms in the category of sheaves alone are natural transformations, so it better be the case that these guys are natural transformations too. Let's look. So here are two different partially ordered sets. The natural category of partially ordered sets has order-preserving functions as its morphisms, so I've shown in blue an order-preserving function between these two partially ordered sets. Okay, great. So if I want to go ahead and extend this to a continuous, into a sheaf morphism, I have to build out that natural transformations. The whole thing needs to kind of commute. All right, so something like this. But in addition, to it being a natural transformation on the level of sets, dragging the sets around. This is a sheaf morphism, natural transformation between two different sheaves. And you can check that it is by checking that each and every possible square, of which there are 3 to check, but you really only need to check 2, commutes. That's easily done. In addition to that, not only does that have to work, the data also have to get dragged along. And that's the additional point that I want to make here. The additional point that I want to make here is, if you're building a sheaf and assignment morphism, not only do you have the natural transformation on the level of the sheaves, you also have it on the level of the data. So if I have a sheaf assignment over here, pick up each of those data values, move them over to the other side, and you see, yes, the data values that I've moved over to the other side are preserved. But it does not have to be the case that within the black arrows, the original sheaves, the data are consistent, just from passing along the transformation. Okay, well that's kind of interesting. And it has a nice little consequence. I didn't write it up as a theorem, but it is a theorem, that if you use a global section on this side, you will end up with a global section on the other. That's simply a consequence of the fact that we had a natural transformation for sheaf morphisms. They do that, and this additional information doesn't disrupt that. Okay, so now we can ask, how does that affect their associated consistency filtrations? These two sheaves are different from the ones that I'd shown you on the previous slides, so let's kind of go through a little bit. This is the consistency filtration for the sheaf on the top there, and what you can see is, all right, well, the one half at the very top, that's consistent with itself, of course. So that thing I had labeled F originally, so that's this cover element. And at some point, once I hit the difference between 0 and 1/2, namely 1/2, I pick up the open set that contains the 0. That's the E and F set. So that's this segment here. And then finally, once I yet accumulate a little bit more error, up to 2/3, I pick up the rest. This guy was the same as before. But now I have a sheaf morphism and an assignment morphism that drags the data from here over to here. What that has to do, if this thing is functorial, is it has to transform the consistency filtration as well. And in fact, actually, that's very clear. What I've highlighted in green, of course, is the entire thing on this side. I've highlighted its image over here. So what the consistency filtration as a functor does is it picks up entire portions of the consistency filtration and moves them, lays them down onto the consistency filtration on the other side. What does this mean? This means that if I want to compute consistency filtration for a very elaborate, large system, I can do it in parallel. I can build it in little pieces and then include together and sew those pieces together. So this gives me the capability to build a very complex, refined model using the systematic approach that I described in my first talk today. It might not be the best choice of data. It might not be the best choice of topology. But you can use the consistency filtration to find the right topology, and you can do so efficiently. So this actually kind of takes us full circle in a sense. We started out, we wanted to find a methodology for working with sheaves such that we would be able to compute efficiently and understand the structure of these models. And in fact, we've basically succeeded at doing that. And now we have the following interpretation. When you build a model of a practical, scientific or engineering system, using the machinery of topos theory and category theory, the way that you do this practically is you make use of the fact that topoi are, in fact, easily built from categories of sheaves, yes, but we can actually build these sheaves, construct them, instantiate them in software. A pre-sheaf on a small category valued in set is really software that is really running, and you can really build. And you can find that category for many real-world systems that are described by systems of equations by a systematic constructive process that scales linearly. It's relatively easy to build. And then once you've done that, you can splice the data in and address forward and inverse problems, asking, how well do the data and the model agree? Make them agree as well as you can. The consistency radius tells you how well they agree. Tells you whether or not you should trust your model or not. Tells you whether you should trust your data or not. And it tells you how to find, infer missing data. The local consistency radius lets you tell where the model and data might be inconsistent, i.e. where in the model, even if I can't actually directly access it, where is it potentially at fault? And so you can look into this and say, finally, then, what is the right system decomposition? What are the right functional blocks, if you will, on which the data and the model are consistent and work together? Effectively, where is the model severable into separate functional units? That is what the consistency filtration tells you. And we know this is reliable for two reasons. First of all, because the consistency radius and filtration are continuous, so they're safe to use with noisy data, safe to use with uncertain models. And the second thing is that since the consistency filtration is a functor, we know that if we make systematic and careful transformations of the model, that this construction comes along for the ride and transforms in a nice way. With that, I hope this was enjoyable and interesting, and I will happily take questions. Thank you.